Hey everyone, welcome back. In this video, we're going to be looking at the vintage Altec 288 compression driver with the 805B multicell. And so this is an 8-cell horn, and then you can see here, I put my hand there so you can get a sense of the scale. The diameter of this compression driver is just over 7 inches. It weighs almost 30 pounds, just the compression driver. And so it's about 2 feet wide and then just over a foot tall, or about 62 centimeters wide, 34 centimeters tall. The horn is quite deep. You can see here it has the kind of the truncated dispersion where it has, if you would take this apart, you'd actually see all the cells combining into one kind of focused area, and that's the fundamental function of the multi-cell horn, is that it concentrates the sound into this rectangle shape and then it disperses into the individual cells. And so Altec publishes the cutoff frequency at 500 hertz and then the nominal coverage pattern at 80 degrees horizontal by 40 degrees vertical. The diaphragm is aluminum, and the diaphragm diameter, voice coil diameter, is 2.8 inches or 71 millimeters. So in this video, we're going to look at the test data and then provide a passive correction network that's going to flatten the response, as well as a high pass filter that's going to kind of eliminate some of the coloration that I was hearing near the horn's cutoff frequency at 500 hertz. So I'll show you that schematic and then also provide some listening impressions after I had developed that kind of correction circuit for home listening. Okay, so here's the raw frequency response. We can see that it's kind of a mid-range centric hump centered at around 2 kilohertz, and then we have a falling response in the upper treble. We don't see any significant resonances near the horn's cutoff. I should note as well is that above 1 kilohertz, it's a gated frequency response, meaning that there's no reflections from the room environment. It's simply the response of the horn itself. Below 1 kilohertz, due to this physical size of my listening space, I had to do an ungated response, which means I'm getting some reflections from the environment. And so to compensate for that, I've applied a 1/3 octave smoothing below 1 kilohertz. Above 1 kilohertz, this is a 24 dB per octave smoothing that you see here. And so this would be very representative of the actual horn's response. And so you can see here that the breakup doesn't really occur until around 13 kilohertz, and we can touch on that in a bit. So now the off-axis colored polar map, this is measuring at 5-degree increments from 0 to 90 degrees off-axis. And so the overall polar map is characterized by a narrowing in the coverage in the 500 to 1.5 kilohertz region, and then it widens out to 120 degrees listening window above that. And so it's very wide coverage. It's quite a bit wider than the 80-degree coverage pattern that's been published. So there's a bit of a narrowing through the lower mid-range, and then it widens out quite wide. And then we see this kind of a combing effect in the polar map. So what this is that if you were to measure directly in front of the individual cell, there's a dip in the response actually in the upper treble. And if you were to carry that back, you'd actually see a rise in the response through the mid-range. So the sound characteristic does change as you move off axis, certainly between the overall sonic character between the mid-range and treble. This is something that's likely unavoidable in this type of a design. So looking at the time domain, you can see here, this is the waterfall plot, and it hasn't been compensated as far as any equalization. So we do see a clean waterfall with that breakup at 13 kilohertz showing up in the response. Burst decay, we are seeing some resonances occurring, whether that be acoustical or mechanical. I'm not sure where the source of that resonance is, but we've certainly seen cleaner results in the past in some other tests there. So now distortion, I measured both harmonic and intermodulation distortion. And so for the 85 and 95 dB test signal, I measured it using a 20 centimeter mic distance. And so the SPL level was set at a 1 meter mic distance for reference. So to allow for the noise floor of the amplifier. So I'm using the Hypex Fusion FA500 amplifier, which is very low noise, but you do need to bring it up out of the noise floor when you're using very high sensitivity compression drivers. And so I did a fixed resistor L pad consisting of a 20 watt, both are 20 watt, 7.5 and 1.5 ohm resistors. And so that attenuates the horn down minus 15 dB. And so that allows me to bring the amplifier up out of the noise floor for this type of distortion measurement. Okay, so generally we see the distortion profile. If we're looking at the 1 kilohertz region, we see that the second harmonic dominates with the higher order harmonics quite low into the noise floor. So we can see that the 1 kilohertz region, the third harmonic is extremely low at 0.015%. Raising the test SPL to 95 dB, again we see the higher harmonics go even lower, and then it's dominated by second harmonic distortion. So doing the multi-tone, we can see here again for the 85 and 95 dB test signal, we have 70 dB of dynamic range for the 1.5 kilohertz region, and then it actually reduces to 60 dB when we're looking at the 10 kilohertz region. If we increase the test SPL, we see that the mid-range performance is unchanged, and so plenty of headroom there through the mid-range. However, for the upper treble 10 kilohertz region, we're seeing the dynamic range reduced to 50 dB. Okay, so moving on to the contour circuit. So the horn, like I mentioned, has a strong mid-range presence with some coloration near the horn's cutoff frequency of 500 Hertz. So I decided to develop a basic high-pass filter along with the contour circuit. I settled on a LR3, so a third-order high-pass filter, to eliminate that coloration, and this was based on just subjective listening and trying to find kind of that threshold to where I could cross it where I didn't hear that coloration. So incrementally raising the crossover point higher and higher until that coloration went away. So I would say that coloration is if you look at this response graph, so the raw response is in red, the blue response is without my high pass filter, with the contour circuit, and then the green is with both the contour circuit and the high pass filter. So you can see here this little bit of a difference in the high pass actually eliminated the coloration that I was hearing, and so the coloration would be occurring at around 350 Hertz. So this is the actual schematic that I had come up with, and so you can see here this portion of the circuit is the third order high pass filter, and then the contour circuit here that brings down kind of that mid-range presence there. So you can take a look at, I'll post a link to the blog in the description there. So you can copy this and use it however you want there if it's for personal use. So you can see here the contour portion is the difference between this red and the blue there. So you can see it's attenuating quite a significant amount, and then keeping that treble unaffected. So after I had implemented the circuit mentioned, I conducted some subjective listening, and so I just summarize my listening impressions on this. So a spatial and enveloping treble, and I believe this was mainly due to the wide coverage that we saw there in the polar map. And then despite the Class D amplifier, the sound had some of that typical H2 smoothness, so it definitely had a nice smooth sound. And anytime I've measured Alnico drivers, I've kind of correlated that the sweet kind of smooth sound is I'm not saying it's attributable because I can't really prove that, but there's been a consistent correlation that there's elevated levels of second harmonic with Alnico drivers, whether it be compression drivers or full range drivers or super tweeters and that. So not sure why that's the case, but it's just something that I've kind of noticed as I've tested a number of different drivers in the past year. So it definitely is missing some upper treble detail. We can tell based on the frequency response there. It's quite a steep fall starting at around 7 kilohertz. And there is some horn coloration that's noticeable across the horn's entire bandwidth. There is a strong presence on vocals even after the EQ was applied. I found it very easy to follow the modulations of the human voice, and so that was something that it did extremely well. And there was some masking of soundstage depth, and so just listening to it in mono, trying to listen for that low level detail, kind of the ambient cues that you hear in music, it was definitely due to the horn coloration, we're getting some of that soundstage depth masked. So overall, the 288 8G with the 805B horn offers an entertaining and enjoyable listening experience if you can get past the slight horn coloration, which is masking the overall clarity. A super tweeter may offer some resolution improvements for the upper treble, but the coloration through the mid-range would still exist. For example, the burst decay is shown below with the contour circuit in place, and so you can see here just how much we're seeing that come through in the burst decay measurement. So perhaps there are ways to improve this, whether that's a mechanical resonance that we're seeing there or whether it's acoustical, but any kind of solution to improve this was beyond the scope of this video. So that's it for today. Vintage Altec 288 with the 805B Multicell. Take care and have a great day.